Boy, it's so windy. Looking at Mom, I got his hair. It's blowing like crazy in the wind. For each point in space, there is a vector. This vector could represent force or it could represent velocity. These objects are all over the place in the real world. This idea is very intimidating because we can't draw a graph because I would need to draw an arrow at every point in space. Something that just makes me feel better about it and like it's not as scary is to try to break down these objects by what category they're in. So you should be able to identify what type of thing that you're talking about by the dimension of the input and the dimension of the output. The OG here, Ice-T, all the way back from Calc 1, all the way back from college algebra, is just a regular old scalar function. Now you got vector valued functions. These functions represent a path in space. The input is one-dimensional and the output is three-dimensional, so we can't see the input axis. We just imagine a particle that moves along this path. We're thinking of the input as being time. So for each point in time, there is a point in space. We call these vector-valued functions of a single variable. We've been thinking of them as vector equations or parametric equations. Level 2 is scalar-valued functions of multiple variables. If the input is two-dimensional, we've been thinking of them as surfaces. And if the input is three-dimensional, we've been thinking of them as density. A vector-valued function that depended on one parameter, like our level 1 example, gave us a one-dimensional object in three-dimensional space. This example in level 3, I have two parameters, theta and z. The graph of this vector-valued function lives in three-dimensional space, and since I have two parameters, this graph is a kind of surface. So this is a hollow cylinder. We jump from level 3, boom, all the way up to level 1000. We got the Big Daddy here. Big Daddy is a vector valued function with three inputs. For each coordinate, x, y, z, for each point in space, there is a vector. This vector is a function. There's a function in the x coordinate, there's a function in the y coordinate, and there's a function in the z coordinate. Each of these functions has three inputs. So the input is 3D, the output is 3D. How can I possibly understand this? There's a total of 6 dimensions. Let's jump in, do some examples, get our hands dirty, see if we can start to grasp what these things really look like. I've got a 2D vector-valued function of multiple variables. This vector-valued function always has 0 in the y-coordinate, so all of my vectors have a y component of 0. This means all of the vectors that I'm going to draw go up and down, have a vertical part of 0. So there's going to be no up and down and no vertical movement in any of my vectors. The x coordinate is equal to the y variable. So the farther that I go up in the y direction, the bigger the horizontal component of my vectors is going to be. It's impossible for me to draw a vector at every point. So what we do is we just draw some of the vectors to give us an idea of what this vector field really looks like. So I've tried to do my best to draw what these directions tell me to draw. All of the vectors are pointing perfectly horizontal because they have no y component. The farther that I go up on the y-axis, the larger the x component of this vector is. Since this vector valued function is independent of x, all of the vectors look the same no matter where you are on the x-axis. So I've just copy and pasted this picture that I made into a few different places on the x-axis. As we move in the negative y direction, the x-coordinate of all of my vectors is now going to be a negative number. So I've drawn all of the vectors pointing in the negative x direction, and they get longer the farther that you go out along the y-axis. That seemed really hard. This seems like something we need to just go really fast and get a computer to verify that we've drawn this graph correctly. In CalcPlot 3D, I'm going to add to this graph a vector field. You can see they give me an M and an N and a P. Those are the coordinates of the vector valued function. So the x coordinate of the function we will call M, the y coordinate we will call N, and the z coordinate we will call P. These fields in CalcPlot 3D tell the computer how many vectors to draw along each axis. So if I change this to 20, it's going to populate a bunch more example vectors along the y-axis. If we drew these vectors to scale, then the picture would be really messy. You can see right here the vectors are starting to overlap each other. So usually when we make these graphs, we scale down the vectors to make them smaller than they really are, just so we can get a better picture for what this looks like. I'll show you what this real picture looks like if you were to graph these vectors how long they really should be. But that's so busy, it's impossible to understand because all the vectors are overlapping each other. These two vector fields are very important. We're going to go on to compare the other vector fields that we study to these two basic kinds. An easy way to understand what a vector field is doing is to imagine that each of the arrows represent forces, and you're going to drop a particle into these fields and let it be pushed around by the forces. Sometimes I'll casually refer to a vector field like this as a spin field or a curl field. You could imagine if I dropped a particle into this, that the forces would just push it all around in kind of a perfect circle. In this vector field, imagine that you had a table and someone was just dumping a jug of water out on the middle of the table. You could imagine that the water would just spread out all over the whole table. This vector field is a model for that scenario. If somebody was just pouring water right in the middle of the table, it would all just run away. CalcPlot 3D will actually do this for you. If you input a vector field, that's what I've done. So just go to Add to Graph, select Add Vector Field. And this is the equation for the spin field. Then if you click on it, it'll drop a particle into this force field and let the particle get pushed around. I claim in this case, the particle will move in perfect circles. Let's find out what happens. You see if I put it farther away from the origin, it'll make a bigger circle here. I'll put it in the third quadrant here. Here's another vector field where I've chosen different values, just kind of some decimal values, and this will kind of make a neat little inward spiral. No matter where I put the point, it will always spiral in to the origin. If you move this time slider, you can actually watch the particle get propelled along. I encourage you to hop over to CalcPlot 3D and add 4 sliders to your graph, and then add this vector field, ax plus by, cx plus dy, and play with these sliders and see how they change the vector field. See if you can get it to make some like I have here where it's kind of spiraling. Or maybe one like this where you could imagine the particle getting pushed towards a line and then shot away from the origin. Or maybe one like this where there's one axis that gets pushed towards the origin and one axis that gets pushed away from the origin. Unfortunately, the dropping the particle functionality doesn't work when you have sliders in the components of the vector function. So if you find one that you really like, you'll just have to choose those values and then type it in manually. I also created Coulomb's law here for the students that are interested in electrostatics. All these negatives account for the vectors pointing towards the origin. I encourage you to calculate the magnitude of this vector, and you should get 1 over the square of the radius. Hopefully you feel more comfortable with the idea of vector-valued functions of multiple variables. It's just a model for a situation like wind, where for each point in space, there is a force. The goal here is to understand how we can do calculus with these objects. The way that we understand how a vector field is changing is with these concepts: flux, flow, divergence, and curl.